All right, so when I go to explain this, one of the things I want to encourage you to consider is that this should probably be something in your notes. We're doing example questions. And if you think you have the correct answer, and I don't always give you homework without the answers, I will sometimes give you the numerical answers to questions like this. I did not in this circumstance, but in the future I often will. The thing I want to impress upon you is the Galilean motion equations are only successful at dealing with one object at a time during one time period with one acceleration. That's important to understand because there are two objects here, which suggests that from the very start of this problem, you'll need two sets of motion variables, one to handle train 1 and one to handle train 2, right? Because the motion variables can only handle one object with one acceleration. So I'm going to start by drawing a quick, simple picture to kind of frame what's happening and to lay out variables. Something that I would strongly encourage you to do as well, as you need someplace, I think, as a framework to kind of get the idea of what's going on. I didn't say they'd be good pictures, by the way. I just said they'd be pictures. So, two trains. They both have an initial velocity of 20 meters per second. One of the trains will have an acceleration of 0, as stated in the problem. The other train is going to have an acceleration that is this direction, that is 0.5 meters per second squared. Under these circumstances, there is no chance that the trains will not meet. Do you understand why I'm saying this? Because if both trains were experiencing an acceleration that was going to slow them down, it is possible that they could stop before meeting. Is it clear that under the conditions of this problem, I don't have to worry about that being one of the solutions? That there's going to be a finite place in between where the trains are now, where they will be at the same place at the same time. Does everybody agree with me? I'm saying this way on purpose because our motion variables are about location, velocity, and time. So I know that in this problem, they will be at the same location at the same time. I don't know where that's going to be, but based on some simple analysis, I bet it's closer to this side than that side, right? Because the one train's slowing down and the other one is not. Are these all reasonable things to think? All right. Train on the left, delta x, v naught, v a t. Train on the right, delta x, v naught, v a t. Okay, so I know the trains are initially separated by 100 meters. So here to here, 1,000 meters. 1,000 meters. I'm just going to write down the things we do know. We know that, and this side will be 1, this side will be 2. Train 1 has a velocity of 20 meters per second. Will have an acceleration of 0 and therefore a final velocity of 20 meters per second since there's no acceleration. All good? Any question about those choices? All right. Train 2 is going to have a velocity starting at 20 meters per second, but will experience an acceleration of 0.5 meters per second squared. I believe that's the only information I know about train 2. Now, there's more that I'm supposed to do here. Step 1, of course, write out my motion variable. Step 2, identify the information that's given. Step 3, choose a direction to call positive and apply it to the problem. I don't care what direction we call positive. I'm going to be consistent with both trains, I think, though. So do you want to the right to be positive or to the left to be positive? So if I make to the right positive, that means train 1 has a positive velocity at the start. Train 2 has a negative velocity at the start. but has a positive acceleration at the start. I'm applying my information consistently across both things. You don't have to do it this way. There are other ways to do it, but I'm going to be consistent. Now, if I look at what I have, I do not have enough information to figure out what's happening to the trains at the onset of the problem. Meaning there's only 2 pieces of information given on the right, and although it looks like I have 3 pieces of information given on the left, I really don't have as much information as it appears. By not knowing how long it takes for the train to go anywhere, any relationship that has delta x in it also probably has time in it, at least any of the ones that are useful. And you might be saying, well, how about 2a delta x equals v squared minus v naught squared, but do you realize this just works out to be 0 equals 0? So not a useful relationship in this regard. But I did say at the onset something that is helpful. Both trains are going to make it to the same location at the same time. So I know the time that it takes the train on the right to get to that location will have to be equal to the time it takes the train on the left to get to that location. I'm just going to put a placeholder in there. I don't know what that time is, but I know that has to be true. In addition, and here's where you have to be a little more thoughtful, train 2 is going to travel this distance, and train 1 is going to travel this distance. Give one of them a name. Give me a variable to use for one of these 2 distances. Y? Okay. I guess. Do you mean like, why should I do that? Or would you like me to use the letter Y?
No, like the letter Y.
Okay. Which one? The one on the left or the one on the right?
The one on the left.
So this is distance Y. That means this is a distance of 1,000 minus Y. Right? Now this doesn't answer my question, but it gets us closer. In fact, I could probably say that train 1 has a displacement of positive Y. Right? That's in the positive direction. Are we all good with that? This is the critical part. This is where you should really be paying attention. We are creating variables that will be common to both trains. Therefore, we could build 2 equations, one for train 1 and one for train 2, that have common variables. That's what we're doing. We're trying to create the condition so that we have 2 motion equations with 2 common variables. Because you guys do know how to solve 2 equations with 2 unknowns. So the right train, train number 2, it's going to travel to the left, that's negative, a displacement of 1,000 minus Y. All good? Now, if I ignore final velocity here, I can put together a relationship that has Y and T in it. In fact, I'm thinking I would use delta X equals 1/2 a T squared plus V naught times T. If I plug in what I know, I will have negative 1,000 minus Y equals 1/2 0.5 T squared plus, well, actually I'll go with minus 20 T. Sorry, bumped it. Any question about those choices?
Why did you choose to ignore final velocity?
Because I don't know what it is. And is it something that will be common to both trains? So those are the reasons I ignored it. And in some cases, you might not know to do that, and you may have to try something with final velocity to figure out that's not really helpful. Yep.
Why the negative in front of delta X?
What direction is that train going?
To the left.
Isn't left negative?
Oh, you're right.
Okay. Just being consistent. So The right train has no acceleration. That doesn't mean I can't use the acceleration formula. I don't have to. There is a simplification, but I'm going to be consistent. And I'm going to use the same relationship. But with the acceleration 0, it is a simpler relationship. Me drawing an arrow through it with the 0 is just letting you know that that whole term is 0 because one of the items in it is 0. That leaves y equals 20t. All good? All right. Do you see a pathway to solve this problem? If not, I'll go on. Go ahead. I'm right here. Go ahead and ask your question.
Because isn't this business from -1,000 minus y? So it's going to be -1,000 minus y even.
That's for train 2.
Oh. I forgot this was trains.
Sorry. It's fine. Can I keep going?
Yeah.
So I'm going to go one more step because I'm nervous. I think between these two, we can do substitution. Right? I have two equations, two unknowns. They are common to both trains. Although I want the answer, I want y, I think it's going to be easier to roll this through the time first. I think it's already, one of them is already solved for y. So I think it'd be easier to eliminate y between these two relationships and find time than it would be to solve for t and plug it into the other relationship. I'm saying that because if I solve the one on the left for t and plug it in, I have to plug it into a t squared and a t. Do you guys see that? I'm going to have to solve a quadratic either way. I think it might be easier to solve this for t first. But there's no right or wrong way to do this. Do whatever you want to do to eliminate one of the variables. So based on that, I will substitute and get negative 1,000 minus 20t equals 0.25 t squared minus 20t. If I distribute the negative sign, distributed the negative sign, move everything to one side. I believe we can work this problem out. There are features of this that I think are important that you may miss because you tend to get disturbed by the big picture here. But I remember that even if I'm not factoring this, which I'm not going to factor this, but the only way I can get a positive sign here and a negative sign here is likely if both of these are negative, which means I'm going to get two positive answers. Now, I'm not going to factor it. I think you'll probably use the quadratic formula or your graphing calculator to get your answer. But I'll tell you this, there's not two answers, right? The trains are going to collide at the earlier time, not the later time. The later time would be what would happen if the one train passed, slowed down, stopped, and then came back and hit the other train from the rear. That's not going to happen. So I think we get the earlier time here, whatever the smaller number is. Okay? I'm not going to do any more of the math. It's just arithmetic at this point. But once you get the time, you can plug back in here to get the location. All right? A complicated motion problem. Once you've seen one problem like this, they are all similar. Two object problems end up being the same. You make two equations with common variables and you link them together. All right. Okay, so the tower's 10 meters tall. I am on the ground. I'm throwing a ball upwards, 15 meters per second. when will the ball be 10 meters above me? Is that a fair simplification of the question? I'm dealing with one object during a time period where it has a single acceleration, the acceleration due to gravity. Just to mess with you guys, I'm going to make downwards positive. Just to prove it doesn't matter. Fair enough? You need to see it. So since we've already done this problem once, one way, we'll do it a second time this way. Delta x, v naught, v, a, t. Camille? What is the displacement of the ball? I don't believe so. We are interested in when the ball is 10 meters above us.
10.
So I think 10. Camille, what is the initial velocity of the ball? I'm having to talk over people who are negotiating their own questions. 15 meters per second. Thank you. Is there anything else I know about this particular situation?
The acceleration.
The acceleration is what?
10.
Thank you. Evaluate them for their direction. Is the ball thrown in the positive direction or the negative direction? Is the displacement that we are interested in the positive direction or the negative direction? Is the acceleration of the ball in the positive direction or the negative direction? Is there a relationship that I could use with the information given that would allow me to solve for the time?
Yes.
Which one is it?
Delta x is equal to 1/2 acceleration time squared plus initial velocity time.
I think we can do it this way. So I'm thinking negative 10 equals 1/2 of 10 t squared plus 15t. This is going to be 0 equals 5 t squared plus 15t plus 10, which is t squared. Oops, wait, there's a negative sign in here somewhere. Nope, they're all positive. T squared plus 3t plus 2. I believe this factors. I believe we can use the factors of 2 and 1. So there will be 2 times. The ball will be at that location 1 second and then 2 seconds after it's thrown.
Wasn't it B plus factoring?
I hope not, because then my answer would be negative.
The initial velocity is negative.
Oh. So I do have a problem. So this velocity is negative because it's negative 15. Okay. Oh, then my signs will be okay. There we go. That's more mathematically correct. Okay. It's still going to be 1 and 2, right?
Yeah.
Okay. Is there anything else to this question? Nope. That is when the ball will be level with my friend, if I had a friend. Camille? Are you sure?
Yeah.
Okay.
Wait, but is that just like a line that it passed? It was level with friend and passed it and connect down when the caught?
I'm sorry, can you put those words back together again? Number 12. The first part of this problem indicates that the ball travels 10 meters in 10 seconds, right? Before coming to rest. I can use that to figure out what the acceleration of the ball is on this ramp, because I don't know it. But we're using the same ramp in part 2 of the problem, so I assume as long as the angle doesn't change, then the acceleration of the ramp will be the same. Is that not unreasonable to believe? Is that okay with all of you? Same ramp, same angle, same stuff? So I think we could figure out what the acceleration is. I will choose a relationship that utilizes everything except for final velocity. That will be 10 equals 1/2 a 10 squared plus, no, I can't use this one because that's got initial velocity. So I'll do the one that has just final velocity. So v t minus 1/2 at squared, or 10 equals 0t minus 1/2 a 10 squared. There we go. Right, there are 5 motion equations. I'm using the one that has these 4 particular things in it. Getting rid of this term. This is 20 equals minus 100a. So a is negative 2/10 or is negative 0.2 meters per second squared. That all okay? Okay, so we don't know what this original speed is either. We're going to have to deal with that. But this is going this way at 2 meters per second, and this is experiencing an acceleration of 0.2 meters per second squared. And now there. And the whole thing is 10 meters apart. We will need how fast the ball was rolled upwards. We don't have it. I think there's enough information over here for us to get it. So I'll use delta x equals 1/2 t v naught plus v to figure out what the initial velocity of the ball was. So 10 equals 1/2 of 10 v naught plus 0. So v naught equals 2 meters per second. Is that okay? Back to over here. Wait, okay. Okay, back to over here. This is 2 meters per second. I will have a set of motion variables for the sled. I will have a set of motion variables for the ball. I don't even know who asked about this anymore. So Noel, pick a direction for positive, up the track or down the track? Down the track is positive?
Yes.
This is the positive direction. So it appears that for the ball, I don't know the displacement. I know the initial velocity is negative 2 meters per second for it is up the track. I don't know the final velocity. I know the acceleration is positive 0.2 meters per second squared. I do not know how long it will take to reach the point on the track. The sled, I don't know how far it's going to slide. I know its initial velocity is 2 meters per second, and its final velocity will be 2 meters per second because its acceleration is 0. Both of those are down the track. They're going to meet somewhere in the middle. I don't know where that is. Would you like to give me a variable that we can use to describe where that is? Is that variable from the sled or from the ball?
Do one for the ball for the position A.
All right, so from the ball to this location is A, which means from this location to the sled is 10 minus A. All right, I've just assigned a variable that I will use for the working portion of this problem. Based on the direction you have chosen as positive, the ball will have to go a distance negative A in time t, while the sled will have to travel a distance 10 minus A in time t. I believe I can come up with 2 motion relationships based on this. And at this point, it's exactly the same as a train question. So you'll have negative A equals 1/2 0.2 t squared minus 2t, and 10 minus A equals 2t. you can use these two relationships to solve for A. Except you want time. So you can use these two relationships to solve for T. Okay? Yep. We're getting outside the window of the amount of time I wanted to use for this. Number 10. You're standing in front of a 1.5 meter tall window. You see a rock pass by window. You see a rock pass by the window, and it takes 0.4 seconds to make it from the top to the bottom. Rock here, passes by the window, rock here. I was going faster here than it was going there. If the bottom of the window is ground level, how high was the rock when it was dropped? I want this height. And all I know is that T equals 1.5. Oh, no, not T, I'm sorry. The height of the window is 1.5 meters, and it took a time of T of 0.4 seconds to make it through the window. Let's talk about the situation of the window. Delta X for the rock as it passes by the window is 1.5 meters. I do not know how fast the rock was going when it enters my field of view. I do not know how fast the rock is going when it leaves my field of view. I know that the acceleration of the rock is downwards at 10 meters per second squared, and I know the time it takes the rock to pass through my field of view is 0.4 seconds. Everything good? Any question about what I've written down? So is up positive or is down positive? Down is positive? All righty. So if down is positive, this is positive, and time, of course, is positive. If I want to find out where the rock began this journey, this is not going to give me that answer. Can it give me something I can use to find that answer? This problem requires that you consider events that aren't described directly in the question. But there are events that occurred before we witnessed the rock. There's the fact that the rock was dropped from here, some height above the window. When it was dropped, it probably had an initial velocity of 0 and fell whatever this displacement is. Would you guys agree with that? So when I consider the information presented about the rock, I can also consider the part of the rock's motion before I witnessed it. I know that the acceleration of the rock will be 10 meters per second squared and will be downwards. I know the rock was dropped some height above the window. So that means it started with an initial velocity of 0. If I had delta X for what occurred above the window, I could just add it to the window's height, and that would give me the answer. But I need another piece of information. For what I witnessed, I can solve for either the initial velocity of the rock or the final velocity of the rock. Is there a way to connect these two parts together? The final velocity of the rock after it fell before we see it is the initial velocity of the rock when we do see it. Right? It falls for a time that we don't see, acquiring velocity. But when it comes into the window's view, it has an initial velocity that it had acquired from falling already. So if I can find out this final velocity, I can figure out how high the window is. I think it's a two-part problem. I would probably use delta x equals 1/2 at squared plus v naught times t. That should be something I can use to figure out this initial velocity. And when I do, take that, put it there, and find out what delta x is. but that's arithmetic. I think I'm good for this. By the amount of feverish writing, it seems we had difficulty with these. At least there was a bunch of easy ones on there. I mean, I don't want to go any further. I can if you want to see it done. Does anybody need to see it done? All right. Is there anything else? I'm going to take that as a no. This is problem number 8, you said, right?
Yeah.
So I find that there's a difference, and there's laying the problem out, and then there's getting an answer. I don't think that those two things are the same. You guys tend to be completionists who believe that getting the answer has value. I am not a completionist. I'm of the mind that completing something provides a certain amount of satisfaction, but setting the problem up and understanding how it's executed is really the goal here. The arithmetic and the mathematics you've done, apparently, and have passed that class. So I like to get us to the point where you've already done something already, and that part is something you can do in your sleep, or perhaps with some struggles, but it's not a big deal. Excuse me. So that's kind of how I like to do this. I draw pictures, and I think it's best always if you do the same. And usually, the strength of your picture tells me how much time you actually spent on the work. If your picture is very elaborate, generally that means the work is poor. If your picture is more schematic, that usually means your work is good, right? Because the picture is just supposed to serve a purpose. So, train number, whatever, we'll call this train 2. This way. And train 1. My understanding is that both trains are traveling at an initial velocity of 20 meters per second. One of the train's brakes fail and therefore travels at a constant speed, while the other train's brakes provide an acceleration that is going to reduce the velocity of the train 0.5 meters per second squared. They want to know where the trains collide if they begin this when they are 1,000 meters apart. All good? All right. Train 1, train 2. Let's build a framework here, okay? Delta X, V naught, V, A, T. Delta X, V naught, V, A, T. The first thing I want to impress upon you is that something I said yesterday and a couple days ago. The motion relationships can only track one object at a time with one acceleration per interval. So if I'm going to write these out, I need to write 2 sets out because there's 2 different objects and they have different accelerations. So while train 1 has no acceleration, train 2 has an acceleration of 0.5 meters per second squared. So these are separate objects. They get separate motion relationships. That all make sense? All right, so now that the chair is out of the way, let's kind of go down and figure out all the stuff for train 1. Do we know how far the train travels? No. Do we know the initial velocity of the train? Yes, it's 20. Do we know the final velocity of the train? Yes, it's 20. It's not accelerating, so it will not experience any change in its velocity. So it starts and ends at 20 meters per second. Do we know how long it takes the train to complete the distance? No. Train 2, do we know how far the train travels? No. Do we know the initial velocity of the train? 20 meters per second. Do you know the final velocity of the train before impact? No. Do you know the acceleration experienced by the train? Yeah. All right. So we have identified the information that has been presented in the problem. That's step 2. Step 3, a reminder that there are vectors in our problem, 4 of them for each object. We need to make a direction. meaning we have to choose one of the directions and make that our positive direction. So Sophie, you brought it to our attention. Would you like the right to be positive or the left to be positive? Okay, so we will establish that to the right is positive for this problem. I'm going to apply that distinction to every object here. There are other schools of thought on how to do this, but I'm going to do this the way I'm doing it this way to be consistent. This is a method. So in my method, every object that we're observing is applied this vector direction for all of its vector values. If you do this, you'll be happier in the future. You'll have less chance of getting the direction wrong. That means both the positive and both the initial and final velocity are positive for the train number 1. Train number 2 has an initial velocity that's negative and an acceleration that's positive. All good? Now, it's this point where we don't have very much information presented, and we're going to need to start inferring things that might happen. For example, these two trains are going to be at the same place at the same time eventually, correct? So I think we can probably state unequivocally that the time it takes for both of these trains to impact the other is the same. I'm putting a capital T there to remind me that this is the time interval for both objects. Although this is interval train 1, this is interval train 2, they both will be moving for the same amount of time. Does that make sense? All right. They're going to meet someplace in the middle, probably closer to train 2 than train 1, because train 2 is slowing down. However, I don't really know where they're going to meet. This is the next thing we need to do. We need to come up with a common variable that we can use for both trains. Something to help us figure out where they meet. So I'm going to indicate that train 2 is going to go this distance. I need a letter to describe it. What letter should we use here? C? All right, you picked C, we'll go with C. That means train 2 is going to travel a distance of negative C. All right, because that's in the negative direction. You need to be explicit about positive and negative. How far does train 1 go in terms of C? Yep.
1,000 plus C.
No. I think 1,000 minus C. Yeah. No, wait.
Oh.
This negative sign is indicative of the direction of the train over here, right? But the value of C will end up being positive. Does that make sense? Okay. I understand exactly why you said that, but this is why, if you'll notice, most of the time I write the numbers out first without sign at all, and then go apply the sign to them. Had we chosen to the left to be positive, I would have put 1,000 minus C here and a negative outside. Does that make sense? But we chose the right to be positive, so that's why we get this. Now, we've done all we can. We've found our motion variables. We have extracted the information from the problem. We have applied direction to our problem. We are now left with the idea that we need to find a way to link these two things together. And this is where I think we generate a motion relationship for each train in terms of C and T. If we can do so, we create the conditions for two equations and two unknowns. For example, for train 1, I'm going to use delta x equals 1/2 a t squared plus v naught times t. It's a little overkill because there is no acceleration, but these equations are designed to work with or without a discrete acceleration. Since the acceleration is 0, this whole term goes away. And we're left with delta x, 1,000 minus c, equals v naught, 20, times t, capital T. All good? Train 2, same relationship, because I don't have final velocity. So negative c equals 1/2 0.5 t squared minus 20 t. Two equations and two unknowns. Do I have to go any further? Is that sufficient? Because you guys have learned how to deal with two equations and two unknowns? Or is there anybody who would like me to go a step or two further? I'll leave it to you to decide. Okay? I would probably look at this and say that it's easier to eliminate C than it is to eliminate T. Unfortunately, we want C for the answer. We're looking for C. Where did the chains collide? But I think it would be easier to solve this to solve and cancel out C than it would be to solve and cancel out T. So I'm going to solve and cancel out C. Does that make sense? This side's already solved for C. So C equals 20t minus 0.25 t squared. And then I can sub that in here for C. Eliminating C between the two. And giving me one relationship that could be used to find the time. Now, this is just algebra. This is no longer physics, but there is an important thing at the end of this I think you should see. I'm going to do the process that's required generally to solve for a quadratic, because this is a clear quadratic. I will first distribute the negative sign. Then I will move everything to a single side of the relationship, giving me 0.25 t squared minus 40t plus 1,000 equals 0. A, B, and C, you can plug it into your quadratic formula and give yourself your answer. What I want to point out is, without factoring this, and I'm not going to factor it at all, but, bless you, this is positive, right? That means that my two factors have to either be both positive or both negative, right? Because they have to be both positive or both negative, the fact that this is negative means that both of the factors are negative, which will give me two positive times. In this situation, they are not both correct. This has become an ongoing problem in my classes. This distinction between what math tells you and the reality of the problem. We're asking the math to tell us when the two trains are in the same location. Okay? There are two times when that is possible. But the reality of the problem is that one train is impacting the other train, right? They're going to have an accident. So I'm pretty sure the smallest time is the one I want, because that's when they are in the same place at the same time first. There will not be a second chance, right? The second chance occurs because if they miss each other, one of the trains has a negative acceleration. Should that not just be brakes, but be the reverse gear of the train, after it stops, it will go backwards and catch up and smash into the back end of the other train. Is that the likely answer we're looking for? No. So, you know what I mean? This became a little bit of banter in my fifth period, but there is the answers, and then there's applying the answers to the reality of the question. They got really hung up on the ball being thrown to the guy on the roof. Really hung up on it. And I don't know why. I don't know what the fixation is. I don't want to do any of the arithmetic, though, okay? The quadratic formula bores me. I really know it bores you. You guys are good, right? You will have to plug that back in here to figure out where this occurs. All right. I didn't record this one, so whoever was wanting to watch this, bummer. This was question 2 and 3. I'll leave this up there for a minute, but we got the acceleration from problem 2. So in question number 10, we're given information about witnessing a rock pass by a window. We're told information about the window, like the window is 1.5 meters tall. We're told that we view the rock as it has been dropped from a height above the window. So we view it as it enters our field of view and then leaves our field of view. I assume accelerating the whole time due to an acceleration due to gravity that is downwards. And that would be, 10 meters per second squared. We're told that the rock takes 0.4 seconds to traverse the window. All good? If I'm only interested in information that's given, I could lay out my variables. And recognize that if downwards is positive, that the rock traveled 1.5 meters with an acceleration of 10 meters per second squared and a time of 0.4 seconds. That clearly tells me that I could figure out how fast the rock is going at the bottom of the interval or how fast the rock was going at the top of the interval, but it doesn't tell me where the rock was launched from. But I believe there's an implied time interval, that there is the time that the rock fell until it reached the window, a distance we don't know about. But we probably know other things about the rock. For example, we know that the rock had an initial velocity of 0 because it was dropped. We don't know the final velocity of the rock, but we know it accelerated for 10 meters per second squared while it fell till it reached the top of the window. And we don't know how long that took. Now, I want this delta x, because I know the window is 1.5 meters high. If I know the delta x for the first portion of the fall, I can tell you how high the rock was above the window when it was dropped. But I don't have 3 pieces of information there. What I'm looking for is a means to get some of that information. And I think the means is laying in the fact that these two problems are connected. Can anybody tell me how they're connected? Go ahead. Sure. The rock starts from rest here, but when it makes it here, the final velocity it has acquired by falling becomes the initial velocity for this interval. So if I can figure out this initial velocity, I could work the problem backwards to figure out how high above the window the rock was dropped. How's that? Is that sufficient, or do you need me to go on from there? Okay, so I would probably find that initial velocity first, using a relationship that doesn't have final velocity in it, and that would be 1.5 equals 1/2 10 t squared, 0.4 squared plus v naught times 0.4. Should be able to use this to figure out what the initial velocity is. 0.4 is squared is 0.16 times 10 is 1.6. Half of 1.6 is 0.8. So 0.8 plus v naught times 0.4 equals 1.5. Let's subtract the 0.8 from both sides and get 0.7 equals v naught times 0.4. So v naught's got to be 7/4. I will probably want a better number than that, but that's what I got right now. I think my arithmetic is okay. I'm kind of going in a hurry. So now delta x equals 1/2 times 10. Oh, wait, I don't want to use that one, do I? Nope. Sorry. I don't have time. So probably not going to reuse the same relationship. I might need a different relationship. How about a relationship that uses these 4 things, though? Is that a better idea? I think so, too. So 2 times 10 times delta x equals v squared, which is 7/4 squared minus 0 squared. That look good to you guys? All right, so that's going to be 20 delta x equals 49/16. Dividing by 20, I get delta x equals 49 divided by, 320? Yeah, I probably would do better to put that as a decimal. Wouldn't you say? And because it's like, what is it, like 0.6 maybe? I don't know. No, it's not 0.6. What am I saying? What's that? 0.153. Thank you. Old. Can't blame that forever, though. The answer is not 0.153, however. That's how high above the window the rock was dropped. We were asked to figure out how high above the ground the rock was dropped. So to get that answer, we have to add the original 1.5 meters of the window to that to get 1.653 meters. So that would be how high it was dropped. That all good? Woohoo! But let's start with the idea that we have a bridge and there's a water level below it. So bridge, water, and we're going to drop a rock and it's going to fall until it hits the water level. We're given a total time of 7 seconds. And we do not know how far the rock drops. We do know that the initial velocity of the rock was 0, correct? We do know that once it makes a splash, that the sound will travel back upwards at a constant speed of 340 meters per second. Agreed? So we don't know how much of this 7 seconds is the rock falling versus the sound traveling upwards. And I'm pretty sure we don't know how tall the bridge is. So let's talk about what we do know. We know for the rock that it has a delta x, an initial velocity of 0, a final velocity unknown, and it has gravity that pulls it downwards at 10 meters per second squared, and that it will take some time to reach the bottom. We also know that after striking the ground, there will be a sound that will travel at 340 meters per second, but that it will be constant, acceleration of 0, and that it will take some time to get back. Agreed? Can we agree that the distance traveled for both is the same? Is that okay? Now, if I want to follow the pattern of the train problem, which is what this is kind of like, do you want down to be positive or down to be negative? Positive? All right. Well, the person who asked gets to choose. So if down is positive, the acceleration is negative. The acceleration is positive. The displacement for the rock is positive. The displacement for the sound is negative. And the velocity for the sound, also negative. All good? We don't know the time. But just like the train problem, if it takes the rock t seconds to reach the ground, it takes the sound 7 minus t seconds to make it back up to the top. Does that make sense to all of you? Kind of see where we're going with this? I think we can kind of pull this together now, don't you? So d equals 1/2 a t squared plus 0 times t, and negative d equals negative 340 times 7 minus t. And with the acceleration being 0, I just left out the 1/2 at squared. I think we got it, right? 2 equations, 2 unknowns. Figure out d or figure out t and plug it into the other. Do you guys see that it's the same problem as the train problem, really?
Displacement and time are swapped.
Kinda, yeah. Because we knew about the time and not the displacement in this one. Alrighty. Good one, though. I like